Okay, we are progressing into sets and logic pretty nicely. We've only got this one last lesson, and then we should actually be able to get into probability. I'm thinking as early as next week, but that will not be on your test. Your exam is next week on Thursday. Look for it to cover sets, truth tables, logic, equivalence, implication, this stuff right here. Also, tomorrow you're going to have your next quiz, but it's over just sets. Okay. So if you have any last minute questions, come on in, ask me about that. So unless anybody has any questions, I think we can just go ahead and get started today. Okay, let's do it. Implication, equivalence, tautologies, contradictions, and testing the validity of simple arguments. And we've already mentioned those vocabulary words, but we're going to bring those up again at the end. So an implication, these are the if-then statements. So we've been looking at propositions that we call P and Q, and sometimes R will be thrown in there. Remember, that's just a statement of fact. It's not a question, it's not a command. But if it's ever in the form if P then Q, we call that an implication. And here's the symbol we use. Now, you might see it as the double arrow, or some other times you might just see it as an arrow pointing from P to Q. We're saying then P implies Q. Now, the thing here to remember is there's not necessarily causation. It's not that one causes the other. And I'm going to go ahead and give you an example of that in just a minute. But an implication is formed when propositions P and Q are linked in the following ways. So the most obvious one that occurs a lot is going to be if P, then Q. Okay, if P, then Q. And then we can also say P only if Q. P only if Q, then P is sufficient for. Okay, and is necessary for. Okay. So if P then Q, P only if Q, P is sufficient for Q, Q is necessary for P. Okay. Now each of these, we know we're dealing with propositions, but we can call them each a specific name. P, the one that implies, is the antecedent. Q is the consequent. All right. Well, let's take a look at an example. Write the implication statement using the propositions P and Q. So my antecedent, John's at work, or excuse me, John is not at work, excuse me. And then the consequent, John is sick. So the implication would be that if John is not at work, then John is sick. Okay. So let's try this next one, B. The antecedent is my watch is slow, and the consequent is I will be late. So how would we write the implication? Yeah, if my watch is slow, then I will be late. There we go. Okay, that's all there is to it. Now, there's not necessarily causation here. It doesn't mean to suggest that something happens. And when we get to the truth table behavior, that's always a little strange to go over, but we'll get there in just a second. Okay, so example 2, identify the antecedent and the consequent in the following implication statements. So if a number is divisible by 10, then it ends in 0. So what's the antecedent? Yeah, a number is divisible by 10. So a number is divisible by 10. Okay. Then, consequent, it ends in 0. If I could write today, that would be fantastic. There we go. Okay. So the if-then statements. Basically, you're just looking for the if and the then parts. Yes, ma'am. You could. It probably wouldn't be a bad idea. Okay. I know numbers. I don't speak well. So. Okay. But yeah, that would be perfectly fine. Okay. All right. Let's try another one of these. I will earn more money only if I work hard. So what's the antecedent? Okay, now be careful. Okay, I work hard is going to be the antecedent here. Because you could say this, if, and there's that key word, if I work hard, then I will earn more money. So this one was just written without the then. So the antecedent will be I work hard. It's an ew. Okay. Okay, consequent, I will earn more money. So it's very possible that you could still take the antecedent and the consequent and go ahead and switch them. Yes, sir?
At the top, where we have all the different implications, we have one that is P only if Q.
Mm-hmm.
So I will earn more money only if I work hard, when I will earn more money to the antecedent if it's P only if Q. And Q's only if in this one.
Yeah, if I will earn more money only if I work hard.
Well, I don't know. Because couldn't you make the statement, I will work hard only if I'll earn more money?
Well, that's what, but you could say.
I mean, I don't know.
If I work hard, then I will earn more money.
Yeah, because that's the way I was thinking of it.
Yeah.
Wait.
So,
Or if I will earn more money, then I will work hard. Oh my gosh, this is.
Yeah.
Let me fluffy.
I don't know. I'm kind of going with the way I have it. Because you could easily just switch it around and say, if I work hard, then I will earn more money. Yeah. Well, that's what I'm thinking. The if, because you're looking at the if-then relationship there, the implication. So I'm thinking.
the only if, it doesn't even.
So Spencer's talking about the only if.
Yes.
Because if P then Q, P only if Q.
Okay, so if we go ahead and say only if, so I will earn more money only if I work hard.
So she got.
Okay.
I will earn more money.
Oh, I see what you're saying. The only, okay. Yeah, because it's in only if, I would probably go ahead and switch those around. Okay, now you convinced me. Okay. Okay, so the only if, there we go. So I will, there we go. Okay. So the flowers will grow only if there is enough rain.
So
The antecedent will be the flowers will grow. Yes, because it's going to be just like the previous one. Okay. Yes, I would agree with that. The flowers will grow. Okay. Only if there is enough rain. Okay. Okay. All right. Okay. Questions? Easy peasy. Okay, well, let's go ahead and take a look at the truth table. All right, now the thing about the truth table when we start looking at these propositions here, again, we've got two truths, two false, true, false for the consequent. But the behavior here, there's only one of these that's going to be false, and it's the true, false. Okay, this is the only one. So if P is true and Q is true, that's a true statement. If the antecedent is false, but the consequent is true, that's still going to be true. And if they're both false, that's still going to be true. Okay. Yes, implication is related to. Now, is that a subset or a proper subset?
So if the proper subset has a line under it.
Okay. Well, which one is it? Now, remember the proper subset cannot be the original group itself. So without the line, that's a proper subset. There we go. Because if it had the bar, a subset can be the group itself. Yes. Okay. There we go. Okay, so here's the thing about the behavior. You know, a lot of people, even when I went through this, just said, okay, go ahead and just kind of memorize what the behavior is. But I'm not really a big fan of that because I want to know why the behavior is going to be that way. So your second page here kind of sets up a scenario that helps us with this. Kind of helps us understand why this is. Okay. So let's say, again, implies doesn't mean suggests. There's also no causation with implication. So why does implication behave the way we see it in the truth table? Remember, out of all of these, true, 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 false, false, true, false, false, what was the only one that's false?
True, false.
It's only true, false. This is the only one that we have to look out for with implication. The rest of these are always going to be true. Okay, so let's go ahead and run through this scenario here. Let's say that here, my statement. If your pet is a dog, then your pet is a mammal. The way we go ahead and classify mammals, right? Okay, what is it? Gives live birth, produces milk, has hair, okay? So if your pet is a dog, then your pet is a mammal. So let's go ahead and start with this first scenario. Let's suppose your pet is a dog. Well, according to this, I mean, that's a true statement, right? Well, if it's a dog, it will be a mammal. So this is looking at the true, true scenario. If your pet is a dog, then it's going to be a mammal. Okay? But now, let's say suppose your pet is a cat. Okay? Well, is a cat a dog? No, so that means the first part is false. But is the pet still a mammal? Yes. So this represents the false true scenario. See, it's still going to be true even if it's not a dog. Does that make sense? Okay. So this one's taken care of. Now let's look at this one. Suppose your pet is a bird. Well, is a bird a dog? No, so that's false. And is a bird a mammal? False. But wouldn't that still be a true statement? If you have a bird, it's not going to be a mammal. Okay? So that's false, false. That's how they can both be false, but overall it's true for what we're trying to say. Now the only one left is this one right here, the true false scenario, the one that's going to end up being false. Okay. Can a situation exist where your pet is a dog, the first statement is true, but is not a mammal? No, there's no scenario where that's always going to happen. So that's why we take a look at it that way. Okay. Yes, ma'am. Depends. A lot of times, what I've seen most often when you're taking the exam and you get these problems kind of come up, really the most I've ever seen anybody have to do is, given a statement, write out the notation and then create a truth table based on that. Okay. But I've never seen it go any deeper than that. Okay. All right. And then I went ahead and put another one on there to try and help out. Okay. Let's say if a figure is a square, then the figure is a quadrilateral. Okay, well, what's a square by definition?
4 sided.
Okay, 4 congruent sides, right? Okay. Then the figure is a quadrilateral. So what defines a quadrilateral?
Has 4 sides.
It just has to have 4 sides, right? Okay, so let's run through those ideas. Suppose you have a square. Well, if you have a square, well, then that's going to be a quadrilateral, right? So that's your true, true scenario. So that is true. So suppose you have a trapezoid. Is a trapezoid a square? No. So that's false, but is it still a quadrilateral? See, that's true, so it's still a true statement. You're confused? Okay, well, what's up?
But I thought it was a truth table. If it was a false, true, it'd be false.
No, if it's true, false. If it's true, false. Okay. All right. So suppose you have a triangle. Is a triangle a square? No. So the first part is false. Is it a quadrilateral? No. So a false, false is still true. Okay. And here's the last one. It's the true, false you got to be careful of. Can a situation exist where you have a square, but it is not a quadrilateral? No, because by definition, a quadrilateral has to have 4 sides, and that's exactly what a square does. Okay. So the first one's true, but the second one's false. There's no way to make that happen. Okay. Does that kind of help? Okay. Because in the original notes, it went through these ridiculous examples, and I didn't think it really helped. So I just created a couple of scenarios myself to kind of hopefully help you understand that. Okay. But here's the thing. The only one you got to be careful of with implication, let's get my highlighter here, is this guy. You're only looking for the true, false. Now remember, implication is very specific in the direction that it goes. So if I were to go Q to P, Q implies P, then again I would be looking for the true-false statement. All right, so the order does matter. Okay, so we went ahead, we talked about squares and trapezoids, all that good stuff. Okay, moving on. Implication, equivalence, tautologies, contradictions, continue. So example 5. So our first proposition, the antecedent, x is a multiple of 4 greater than 1 but less than 20. Q, the consequent, x is an even number greater than 1 but less than 20. Okay, so write the truth sets. And Emily was asking about this the other day. What are we referring to when we say truth sets? Yeah, like the set with the actual elements, right? Okay, so I need a number greater than 4, or excuse me, greater than 1, which is a multiple of 4 and less than 20. So what would that be? It's got to be a multiple of 4, so we'll start with 4. Okay. 16, and we'll go ahead and stop there. Okay. And then the consequent, x is an even number greater than 1, but less than 20. So now I'm going to start 2, 4, 6, 8. Who do we appreciate in math? Wow, that did not go over as well as I thought it would. I kind of saw, I know I got one person go, yay, but, you know. No, okay, wait a minute. Yeah. Moving on. 14, 16, 18, but less than 20. Okay, so we'll stop there. Okay, state the implication. P implies Q. So how would you like me to write this? Okay, if x is a multiple, okay, of 4 greater than 1 but less than 20, what did you say, sir?
That x is an even number.
Then x is an even number. Greater than 1 but less than 20. Less than 20. Okay. And, you know, there's different variations on how you could have said it. X is a multiple of 4 greater than 1, but less than 20, only if x is an even number greater than 1, but less than 20. Hello. Yeah, come on. Mm-hmm. Talking today's homework, right? Okay. There you go. All right. So put the elements of P and Q in the Venn diagram to show the relationship between P and Q. Now remember, we're referring to a proper subset. Okay. So what elements of P also belong to Q? Well,
4, 12.
yeah, all of them, right? So right here, 4, 8, 12, 16. And then inside Q, I'm going to go ahead and put the rest of those. So 2, 6, okay, 10, 14, 18. And am I missing any numbers? No. Okay. There you go. So it represents that proper subset. Okay. Okay, good, 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 good. And let me do this. Okay, so now we're going to talk about the converse, the inverse, and the contrapositive. The converse of an implication is formed by swapping the antecedent and the consequent. So the converse of P implies Q is simply Q implies P. Okay, the converse is just to switch them. The inverse of an implication is formed by negating both the antecedent and the consequent. So P implies Q becomes not P implies not Q. All right, and now we're building up, so the contrapositive will be to do both, to switch them around and what? And negate them. There we go. So if I have P implies Q, then this is going to be not Q implies not P. Thank you very much, man. All right. So let's take a look at an example here. It says, example 6, a quadrilateral is a rectangle. That is my antecedent. And Q, the consequent, a quadrilateral is a parallelogram. State the implication of the propositions P and Q. So I just want P implies Q. Say again, man.
If a quadrilateral is a rectangle, then a quadrilateral is a parallelogram.
There we go. Okay. Exactly what I put. Now the converse is just to switch the two. Okay. Alejandro, what would you say for that one? This time I want if Q, then P.
If a quadrilateral is a parallelogram, then it's a rectangle.
Okay, then a quadrilateral is a rectangle. Would you guys agree? Okay. And I started abbreviating when I wrote this out. If a quadrilateral is a parallelogram, then a quadrilateral is a rectangle. Okay, good. C, state the inverse. Now, while the converse switches the antecedent and the consequent, the inverse simply negates both of them. Okay, so Evelyn, can you tell me not P implies not Q?
If a quadrilateral is not a rectangle, then a quadrilateral is not parallelogram.
That's exactly right. If a quadrilateral is not a rectangle, then a quadrilateral is not a parallelogram. Okay. And then our last statement here, the contrapositive. Now remember, this one does both. It'll not only switch the antecedent and the consequent, but it'll negate them. Okay. John, can you help me out with this one? So I want not Q implies not P. I'm sorry, sir? Okay. So we've got the implication. We got the converse and the inverse. Here are my two propositions. P is the antecedent, Q is the consequent. So we're using these guys right here. Let's see if I still have the highlighter. Yes. So we're using these guys right here. So I'm looking for the contrapositive. Not Q implies not P. I'm sorry? There's one thing you're forgetting, sir. Remember, what's that little sideways L? Starts with the N. Okay. So the negation. So we want to say if a quadrilateral is not a parallelogram, then quadrilateral is not a rectangle. Okay. Perfect, perfect, perfect. Okay. All right. Okay, any questions on that? Okay. Anybody having a hard time? No. Okay. Well, we've talked about implication. Now let's go ahead and talk about equivalence. Okay, so these are the if and only if statements. Okay, this is where it goes in both directions. So if P implies Q is true and its converse, Q implies P is true, okay, if both of those are going to be true, then the implication is going to be true. Okay, so let's go ahead and take a look at our table here. Well, let's get our example 7. I will buy you an ice cream. You get an A on your math exam. So the equivalence, I will buy you an ice cream if and only if okay, if and only if you get an A on your math exam. Or I can put IFF. Okay, good. Now, let's talk about the truth table. Okay, we want to go ahead and complete the following. Now, what I would go ahead and do, in order to kind of see the behavior of what the implication is going to give us, I would go ahead and add 2 other columns here. In fact, let me go ahead and do so with this. There we go. Okay. I would actually go ahead and show the implication in both directions because you need the implication in order to show the equivalence. So I would say P implies Q, and then Q implies P. Okay. So take about 30 seconds to fill in those two columns. Okay. Then if you're feeling ambitious, go ahead and fill in this last column, the equivalence. Okay. Let's see if we can all get on the same page. Okay, now remember the behavior, the order that you're doing this in. First I want P implies Q, right? What was the only one that we had to worry about? The true false. Okay, so true, false. So this one should be true, false, true, true. Did everybody get that? Okay. Now you're going in the other direction. Okay, so again, if Q implies P, again, the only one I'm looking for is the true false. So going backwards, that should be the only false one. Because see, we first have a truth, and then we go to false. Is everybody okay with that? Okay, so the order absolutely matters. We have true, true, true. Okay, now here's my question. What's the equivalence going to look like in that last column? What should the first one be? Y'all agree true? What about the next one? False. What about the next one? Next one? Now, why was the top row and the bottom row, why did you decide true? Like what? There you go. Remember what I highlighted up here? If P implies Q is true and Q implies P is true, then this is going to be true. So that's why I went ahead and had you write out some extra columns here, because I think that's going to make it easy and help you understand why we have that behavior. Okay, here, oh, it's still on the deal, so let me grab that highlighter again. Okay, so true, 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 true. Okay, so in one direction, for those other ones, we didn't have both true, so that's why we had to go ahead and take that out. Now it says over here, the equivalence is related to P equals Q in sets. Okay, so what should I shade here?
Or like, what do you mean?
For the Venn diagram, to represent equivalence. Just the circle inside the...
Well, just like the circle.
Yeah. Okay, so this guy right here.
Because the other way we could have thought about it is like, if P is true, then Q has to be true.
Mm-hmm.
So if they're both true, it's true. But if only one of them is true, it'd be a false statement because they're like equivalent to each other.
Yes.
That makes sense.
Mm-hmm. So is everybody okay with equivalence? Okay. So what you're going to want to look for in equivalence, if they're both true, that's true, or both false, that's true. Or if you do happen to forget, go ahead and add on the implication. Okay. If you're trying to show equivalence, show P implies Q and then Q implies P. And from there, you'll remember that behavior and you should be able to get it done. Okay. Good, good, good. Well, let's try this one. Example 9. Madrid is in Spain. The consequence, Spain is in Europe. Write the equivalence statement for the above propositions. Okay, Samir, what do you got? Madrid is in Spain if and only if Spain is in Europe. That's it. That is exactly right. Okay. Now, this next one, I'm not going to go ahead and worry about. If you guys want me to, this is just a proof of it, but IB is never going to ask you to prove these statements. If you want me to show you, I will. Other than that, I'm just going to go ahead and move on to example 11.
Example 11.
Okay. Does anybody want to see it? Does anybody want me to have it written out for tomorrow when you come in? Eli, you do?
No, I think we'll be okay.
Oh, Spencer, you do? Okay, so I'll have that written out for tomorrow. Okay. All right. So example 11, construct truth tables for the following compound propositions. All right. So what does this sideways L mean? That's not. That's a complement in sets. That's the negation. What is this one right here? The upside down V. Okay, that's a conjunction, so we're talking about an intersection, right? Okay. So let's see here. We already have P and Q, so it's progressive. I want not P, and then I want the conjunction of the two. Well, what does a negation do?
Flips it.
Yeah, it just flips it. So if it's true, it becomes false. False becomes true. So false, false. True, true. Now, think about the behavior, but don't say it out loud. Let's see if everybody can remember. What's the behavior for a conjunction? Is it at least one truth, or do they both have to be true? What do you? Don't say it out loud. That's okay. Okay. So say what you're going to say, Eli.
Or don't they both have to be true?
They both have to be true. There we go. So here, I'm wanting to show not P and Q. All right. So I'm going to go ahead and mark those two right there. So true, false. That's a false. False, false. What about a true, true? That's a true. For a conjunction, the result is only true if both statements are true to begin with. And then we have a false, true. That's a false. Okay. Good, good, good. Excellent. I'm sorry?
Laid it out on the table.
That's the truth. That one was kind of weak, but I'm going to stand by it. Okay. All right. So let's take a look at this one. And here's that vocabulary word that I introduced over the past couple of days, tautology. Okay, so we have that P is going to imply the union of P and Q. All right. So see, of course, I have a P column, I've got a Q column, I've got that quantity, and then I've got the implication statement. Remember, they're always building, so basically you're going to need a column for everything. Would you guys like to try this one on your own? No? Okay. Zoe, is this the inclusive or the exclusive? This is the inclusive. Okay. What does that mean? Sure. Okay, Gabby. There you go. One or the other or both. Yes. One or the other or both. Okay. In contrast to that was this. That's the exclusive. That's one or the other, but not both. Yes. Okay. So let's see here. What about a true, true? True. True, false? True. False, true? True. At least one is true in an inclusive, but false, false is false. Okay, now again, the order in which you do this is very, very important. I want to show that column P is going to imply this quantity in the third column. Okay, so let's see if I still have the highlighter up, and I do. So this one and this one. Okay, now remember, what's the only one we have to look out for? If it's first true, and then the second one is false. But I'm looking at this, true, true is true, 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 false, true is still true, and false, false is still true. Okay, so this is what we refer to as a tautology. This is a correct statement. A compound proposition that's always true, regardless of the truth value of the individual propositions. Okay, so if your final column ends up being nothing but truths, that's a tautology. Okay. And that means that the statement you are looking at is correct. Okay. Now, use the truth table to show that the compound proposition P or not P is a tautology. All right. Well, not P is just changing the truth value here. So that's false, and that's going to be true. Now, what about this? Again, this is the inclusive or, so at least if one is true, the outcome is true. And again, here, both are true, so I will say that is a tautology. Okay. What if I get at least, they're all true, but one false? I cannot say it's a tautology. Okay. There we go. Good, 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 good. I think we're actually almost done. Okay. We can go ahead and at least introduce the other one before I go ahead and pass back some papers. Now, a compound proposition that's always false, regardless of the truth value of the individual propositions, that is what we call a contradiction. Okay, so use a truth table to show that the compound proposition, the conjunction, the intersection between P and not P, is a contradiction. And you know what should have been? Instead of P, I wish they'd used B. B or not B, to be or not to be. Come on, man, I could have done so much with that. Peyton doth view the view screen. I don't know. It's English. I don't know. And I do math. I don't do words. Okay. All right. Use the truth table to show that this is a contradiction. All right. Well, the negation. Now, in place of the sideways L, what can you also have? Just that little tilde, okay, the little curve. Okay. So this one would be false. This one would be true. So now, what is it here? Okay. Both have to be true in order to get a truth, right? So true, false is false. False, true is false. So see, I ended up with nothing but falses. That's a contradiction. Okay, so these are very specific. If you get nothing but truths in your final column, that's called a tautology. That means it's a valid argument. Okay. If you get nothing but falses in the last column, we call that a contradiction. That is not a valid argument. Okay. I got 201. What do you think? Should we go for it? I did want to go ahead and pass back some papers. Well, let's. I like it. I like it. Okay. Sure. Well, let's go ahead and vote because this is still a democracy, even for a short while longer. Okay. It's going to be a dictatorship under Trump. Anyways, I'm sorry, not stepping on anybody's toes if you like Trump, but anyways, how many people want to go ahead and work the truth table? Okay. Well, I guess there's no reason to ask the other question. One person, but we will start here tomorrow. Yes. All right. Thank you very much, guys.